We have three variables, x, y, and z. Their sum is equal to 1. The power sum of degree of 2 is equal to 2. Power sum of degree of 3 is equal to 3. And what about the power sum of degree of 4? Could it equal to 4 or something else? So this problem is from the book Abstract Algebra by Dummett and Foote in the chapter of Galois groups of polynomials, the study of symmetry. And in fact, we can solve it without using too much abstract algebra. First, let me use some notation for our own convenience. Let's denote alpha 1 to the power of k plus alpha 2 to the power of k, where k is a positive integer, all the way up to alpha n to the power of k. Power sum of degree of k, denoted as pk. In this case, p1, p2, p3, right? So let's look at the monic polynomial. X to the n plus an minus 1, x to the n minus 1, all the way up to a1 times x plus a naught. So it can be factored into x minus alpha 1 times x minus alpha 2, all the way up to x minus alpha n. Alpha 1, alpha 2, alpha n are the n roots, including complex roots. Maybe repetitive, maybe not, but doesn't matter. That's okay. So can be expanded into x to the n, right? Basically the same thing as this one, just the relation between the coefficients, right? Minus s1 times x to the n minus 1 plus the alternating series s2 times x to the n minus 2, alternating. The sign is determined by n, negative 1 times n times Sn. And so the relation is that an minus 1 corresponds to negative S1, and an minus 2 corresponds to S2, where S1 happens to be the sum of the roots, alpha 1 times plus all the way alpha n, where S2 is equal to the sum alpha j1 times alpha sub j2. I'll explain what that means. So 1 less than j1 less than j2 less than or equal to n. So what this means is that, so this sum is composed of each term, right? Where each term in this sum is the product of the two variables where the subscript satisfy this inequality, right? Of course, within 1 and n, right, all the possibilities, right? Subscript, right? 2, 3, 4, 5, 6, 10, so on and so forth. All the possible combinations. Right? But since alpha 6 times alpha 10 is the same as alpha 10 times alpha 6, so that's already the same. So we say the first subscript is less than second subscript. And that's why we add this requirement. And so the same logic where Sk is equal to the sum alpha j1 times alpha j2 times all the way alpha jk. 1 is less than j1 less than j2 less than jk. Same reason, denoted as sk, because each term is degree is just k. And of course, Sn is just simply alpha 1 times alpha 2 all the way up to alpha n. And if degree of n, if the degree is larger than n, what happens? If r is larger than n, then we define to be 0. And of course, we define S naught to be 1. And it's easy for us to verify that each sk is symmetric. So which means if you interchange any two variables, it'll be the same thing. That's easy to verify. And of course, if I substitute alpha 1 into this equation, I have 0. I also into this equation, the same thing. Right? So 0 equals to alpha 1 to the n minus s1 times alpha 1 n minus 1 plus s2 times alpha 1 n minus 2 all the way. Negative 1 n sn. 0 equals to alpha 2, right? Substituting here gives me 0. So also substitute into this equation, alpha 2 to the n minus s1 times alpha 2 to the n minus 1 plus n s2 times alpha 2 n minus 2 all the way. Negative 1 n sn. Right? All the way. 0 equal to alpha n minus s1 alpha n minus 1 plus s2 alpha n minus 2 all the way sn. And so when you sum them all up, 0 is equal to the alpha 1 to the n plus alpha 2 to the n. That's the power sum of degree of n, Pn, right? And minus S1 common factor, right? Alpha 1 to the n minus 1 plus alpha 2 to the n minus 1. That's the power sum of degree of n minus 1, Pn minus 1. Right, plus S2 times, likewise, Pn minus 2, right? Power sum and n minus all the way. So the last term I have n times negative 1 to n Sn. And what's even better is that according to Newton or Gerard-Newton formula, it says even if we don't have n, even if we have k, where k can be bigger than n or less than n, we can always also have this identity as well. Also, 0 is equal to pk minus s1 times pk minus 1 plus s2 pk minus 2, alternating series where the subscripts add up to k every time, right? All the way. Negative 1. I should k times negative 1 to the k. Sk. Right. K doesn't have to be equal to n. Right. It could be less than n, could be bigger than n. Now all I have to do is to determine what's the value of P1, P2, P3. I have 3 roots, right, instead of n roots, but power sum of k, power sum of 1 is P1 is equal to 1. P2, power sum degree of 2 is given to be 2. P3, given to be 3. Right, and so what's S1? S1, the sum of all the roots to be 1. Right, I'm going to determine S2, determine S3, and finally, in order to determine P4, right, that's my ultimate goal. Right. So determine S2. Right, what's S2 equal to? So 0 is equal to P2. I'm going to set k equal to 2. 0 equal to P2 minus S1 times P1. S1 times P1. 1 times 1. Right? Plus 2, positive 1. 2 times S2. So S2 is equal to P2 is 2, right? P2 is 2. 1 minus negative half. Negative half. So set k equal to 3. 0 is equal to P3 minus S1 P2 plus S2 P1. Then minus 3 times S3. Right. P3 is equal to 3. Right? P3 equal to 3. S1 is 1. P2 is 2. Right? P2 is 2. S2 is negative half. Negative half. P1 is 1. So S3 is, 1 minus half. Half. Positive 1 over 6. Right? What's P4? P4. 0 is K equal to 4. P4 times minus S1 P3. S1 P3 plus S2 P2 minus S3 P1. Then plus 4 times S4. Right? But the question is, what's S4? S4, like I said, I have 3 roots. Now, every time R is bigger than the number of roots, SR is equal to 0. So 4 is bigger than 3, so S4 is automatically 0. Right? So in that case, 0 is equal to P4 minus S1, 1 times P3, 3, plus S2, negative half. Negative half, P2, 2, minus S3, 1 over 6. Yes. So in this case, P4 is equal to negative 3, negative 1, negative 4, negative, positive 25 over 6. Yes, 25 over 6, not 4.